Recording started. So let's start with what is corrosion. So I think many of you would have heard the word of corrosion and have seen rust somewhere in your life. So corrosion, multiple people have tried to, these are textbook definition. So for example, the first definition by Denny Jones, he's saying it's a destructive result of a chemical reaction between a metal and environment. By metal, what we mean is it can be a metal or an alloy. So an environment, it is not to be correct. It is not correct to say it is just a chemical reaction. Of course, it is a chemical reaction, but it's specifically an electrochemical reaction. So another definition is that due to reaction, it can be anything. So we want to, and as you can see, the definition is becoming broader and broader. You can even say it is environmental degradation of materials, not just metals. But in this course, we will try to focus mainly on metallic materials. So this field of corrosion lies at the intersection of electrochemistry and metallurgy. So we need to understand, have a fundamental basic of both metallurgy and electrochemistry to understand corrosion and try to tackle corrosion. So there are several examples, like from trivial examples to examples in critical application. For example, you can see a cracking of a heat exchanger tube in a nuclear power plant can be catastrophic, but a rusting of an iron pipe that is lying somewhere might be just a trivial example. So, and we have, so one thing we need to note here is that the deterioration of material by physical causes, such as light or just the temperature, is not corrosion, but there are other examples where you have some particles impinging, eroding the surface, that is, there is erosion, galling, or wear that happens due to friction between two rubbing surfaces. So those are not considered within the scope of corrosion. So this is what is corrosion. Then why do we care about corrosion? I'm going to give you 4 reasons why we should care about corrosion, starting from cost, safety, and third is carbon footprint, and fourth is materials conservation. So cost of metallic corrosion, you can see, if you see the global cost of corrosion every year, it is around 2.2 trillion US dollars, which is almost 3 to 3.5% of the global GDP. When you consider the value, it's very high, and this includes only the direct cost due to corrosion, not the indirect cost, because some corrosion failures can lead to stoppage of work, leads to loss of time. Those are not accounted in this 2.2 trillion. So it is much more high. You can see the cost of downtime or the cost of material, labor, and maintenance. These are not included in this 2.2 trillion. That means the cost of corrosion is even higher. So if you want to read more about it, there is a white paper that is there in the Student portal where you can see and there is also this damage to persons and environment that are not repairable, like hospitalization due to some corrosion failure is not accounted in this cost. So it's a very costly endeavor. So we want to prevent corrosion because it's really costly to do it. Sorry. So then coming to the safety aspects of corrosion, that corrosion can have catastrophic consequences. For example, these are boilers that are used in these power plants that use thermal energy and convert it into electrical energy. These pressure vessels and boilers can undergo corrosion attack. Ships and submarines, obviously, as we will encounter a very obvious environment that causes severe corrosion is seawater. So submarines and ships are always subjected to corrosion, and we are always trying to fight corrosion and solve these problems. And oil and gas pipelines also suffer from corrosion because these crude oil that is used there or the natural gas can be extremely corrosive to the material. And there is also corrosion happening in nuclear power plant where it might also be combined with irradiation effects. Like it is not just the environment, you also have radiation that can also influence material degradation. And nuclear power plants also generate a lot of waste that we need to dispose somewhere. These wastes cannot be just thrown away outside as it can be very hazardous. So we need to store it somewhere until it becomes safe to be sent out. So these waste containers also are subjected to severe corrosion, and these big structures like bridges, for example, this is a bridge collapse in the US that was blamed on corrosion. This is another example in the United States where oil and gas pipeline burst to cause this fire and also led to some fatalities. And aircrafts. Aircrafts are also subjected to severe environment, the aircraft body, and to prevent icing, we also wash it with some salt waters that can also corrode this material. So this is one of the examples where the fuselage of the aircraft just flew away in flight, and subsequent failure analysis revealed that there were corrosion near the crevice corrosion near the rivets that led to this failure. Fortunately, there was no fatality, but if it happened during a very high flight, because this was an island hopper that flew between two islands between Hawaii, so it was not flying too high. If it happened at very high altitudes, then all of the passengers would not have survived. So next, coming to carbon footprint, as we all know, we take an example of steel. Steel making, the process of making steels from iron, starting from iron ore, is an energy intensive as well as carbon dioxide emitting enterprise. If you see, the steel production has been in the rise because we are keeping on building and improving our infrastructure, but we are also replacing. If you see, there is almost 490 million tons of corrosion happening while we are producing at 1952 million tons. So almost 1/4 we are trying to replace the corroded material. So that is increasing the carbon footprint. If we want to reduce the are we part of this class? Or?
Yeah.
Okay. So replacing corroded metals increases the carbon footprint. We need better corrosion management practices to reduce the carbon footprint of corrosion. If you're interested to read about how this carbon footprint works, there is a link to the paper that was published in 2022 that you can read. This is also related to the previous fact, but it also means that if we are not recycling this back to the steel, because we start from iron ore, which is basically iron oxide, and then we use these processes in the steel mill, you get these materials that are used in a car or in some underground pipelines, they corrode and they go back to their native form. So you see, to reduce the iron ore into iron, you expend a lot of energy. Per mole, you are spending around 156.5 kilojoules, but corrosion happens, or corrosion of steel in water, then you are releasing a huge amount of energy, which is even higher than this. So you are wasting a lot more energy than you tried to spend to produce steel from iron ore. So, but we do not have really abundant iron ores. So once we have exhausted, unless this rust can somehow be recycled back, and then you put this rust into this process and keep the material loop closed, then you are not, if you are not doing that, then you are going to get rid of all iron ore and there will not be any iron left if we keep on corroding and making steel out of it. So more reasons to protect the materials against corrosion. So the aims of the lecture, as I said, that the course is named as Advanced Corrosion Science. It assumes some familiarity with the basic concepts, but given people, the students in the class might come from different backgrounds, might have different levels of familiarity with the corrosion. So the first two lectures will try to review corrosion, under corrosion science fundamentals, talk about corrosion thermodynamics and kinetics, and then we will talk about different methods that are used to monitor and understand corrosion phenomena, and then we will talk about an important concept of passivity that makes some metals develop a layer and be stable, and then that also leads to another problem called as localized corrosion, because it is even more insidious problem, because when a corrosion occurs locally in a region, then it can pose a threat to the structural integrity of the material. Then we will also, this is all low temperature, then we will talk about high temperature corrosion, the theory behind it, because even though the basics will remain the same between aqueous corrosion and high temperature corrosion, the mechanisms can be different, because with higher temperature, the kinetics and the diffusion will start to play a more important role, and the underlying microstructure, because these metals have a microstructure that runs across different scales, they can also continue to evolve as oxidation process is happening. And then we will introduce you to the idea of environment assisted cracking. This is because in most applications for structural materials, we are having both stress and the environment acting on the material together. So to understand the combined synergistic effect of stress as well as environment, we'll be talking about stress corrosion cracking, corrosion fatigue, and high temperature stress corrosion, which will also, we will superimpose high temperature stress and the aggressive reactive environment. And then, since this is a graduate level course, we would go and try to introduce overview of new topics, like new research topics that are emerging. For example, there is a huge amount of research happening on additively manufactured alloys and high entropy alloys, and we are also want to produce energy in a clean manner. So we will be discussing about corrosion in batteries, fuel cells, and there is an increasing use of computational modeling, not just experiments, to try to model the corrosion phenomena across length scales, and obviously the new emerging topics of machine learning and artificial intelligence, how they might be useful in predicting corrosion and predicting lifetime of these engineering components that might be subjected to corrosion environment. And finally, these are one thing we need to increase the awareness among engineers and material scientists about the important problem of corrosion and the importance of corrosion protection. And I hope I'll be able to convince you that this is an exciting topic by end of this course. I think you can read these learning outcomes for your own purpose. So this is a preliminary schedule. So today I will introduce these topics, what are these, and the first two lectures will be just to fill in those people who have not taken any corrosion course earlier, to give them the required basics so that the entire class comes to the same level with respect to the basics. So the first two lectures will be on corrosion basics. For the second lecture, it's on 6th November, I will not be here in person, so I will post the pre-recorded lecture during the time that you are expected to watch before you come to the class on 13th. And we also have a guest lecture in the early January from Professor Shaule Guo from Colorado School of Mines. He will be talking about corrosion in nuclear waste disposal, the waste that are generated out of nuclear power plant. So it will be a shortened lecture, but I will have to, since the class timing has changed, I will have to check with Professor Guo and let you know how we can reschedule the class according to the class timing. But this will be a Zoom lecture. So, but there will be an in-person class, but we will play the lecture with the professor, and then the last three topics will be these new topics that are research topics, more for your familiarity. And I have not put the lecture, the last lecture, which is kept as backup in February. If there is any topic that needs to be covered or discussed, we will keep the lecture on 5th of February for that. So that's not there in this list. So now I'm going to give you an overview of different chapters that were listed. So corrosion basics, we will be talking about what are the requirements, because corrosion is a process. For this corrosion process to occur, what are the requirements that we need, and to demonstrate the electrochemical nature of corrosion, and introduce you to different forms of corrosion, because corrosion can take different forms. And then we will cover corrosion thermodynamics. We will talk about the concept of electrochemical potential. We will introduce you to electrochemical interface, the interface structure, and then the equations that describe the equilibrium between the electrolyte and the metal, the Nernst equation, and then we will introduce you to the concept of Ford-by diagram and how we can predict whether this corrosion is going to happen at this given condition or not. And then we will move on to corrosion kinetics, because thermodynamics and kinetics are two sides of the same coin. So we need to understand both of them together to understand this entire process. So we'll discuss about the Butler-Wallner equation that will plot the Nernst diagram and the mixed potential theory that will set you up for the future chapters. And then I will also introduce you to different approaches to tackle corrosion problems, such as changing your alloy composition, designing new alloys, or usage of coatings, inhibitors, and cathodic protection. And finally, we will talk about different corrosion measurements, starting from simple mass loss. You immerse this material and take it out and measure how much mass loss has happened, or mass loss or mass gain that might happen with this. And then we have electrochemical methods, including polarization, electrochemical impedance spectroscopy, and electrochemical noise, etc. So this will be the goal of the first chapter. So the second chapter is surface science and applications to corrosion. So here, because corrosion is basically a phenomenon that happens at the surface, so we need to understand what is happening in the surface more closely, starting from atomic level, like atomic arrangement on the surface, how they can, but we need analytical tools to study that. So this part of the lecture will introduce you to analytical tools that are used in corrosion, the surface analytical tools, including the scanning Kelvin probe and scanning tunneling microscopy, X-ray photoelectron spectroscopy, and X-ray absorption near spectroscopy. This technique is a very interesting technique where you can see in situ what is happening in the surface as we are polarizing to a particular potential. So this can be done in situ, and even these experiments can be done in situ. We can see atom by atom what is happening on the surface, how the oxide is forming. These are ultra high vacuum techniques. So we will be discussing some key papers to give you a taste of how these surface analytical techniques can be leveraged. So The first chapter, I said we will discuss some conventional technique like mass loss and some electrochemical methods. And the second chapter will focus on surface analytical tools. And the third chapter is about really a new research topic that has emerged in recent years, is that non-electrochemical methods that can complement the conventional electrochemical experiments, including this atomic emission spectroscopy, spectroelectrochemistry. Was developed in Paris by Professor Kevin Ogun, where you have a flow of cells where the electrolyte is flowing. You have this material here. As it is corroding, you see at what rate, if you have an alloy of magnesium and zinc here, you can conclude, okay, how much magnesium is dissolving? I have a total dissolution rate, but how much is magnesium dissolving and how much is zinc dissolving? So in an alloy, you have multiple elements. They all, what you measure will be the total, the mass loss or anything you will measure is a total corrosion rate. We don't know how much the alloy composition is changing because different elements might dissolve in the alloy, can dissolve at different rate. And this technique is a very powerful tool which uses this ICP atomic emission spectrometer, which can produce plasma, and we can see how much magnesium or zinc, or this can be applied to any material. So this is an example from a paper. And another technique we will be talking about is respirometry, that was originally developed in the chair of surface science and corrosion at FAU, which can monitor how much oxygen reduction reaction, which are the main cathodic reaction, and oxygen reduction reaction and hydrogen evolution reaction that happen during corrosion. So we can use this respirometry that monitors in real time how much hydrogen is evolving or how much oxygen is consumed during the reaction. So it can be an indirect measurement of corrosion rate, because if you immerse a material or if you put it in an environment without connecting to any electrical circuit, the rate of cathodic reaction should equal the rate of anodic reaction. So if you want to know the dissolution rate without actually doing it, you can use this respirometry method that uses a simple concept of oxygen sensor and pressure sensor. So to measure how much oxygen got reduced and how much hydrogen got evolved during the process, then you can back calculate how much corrosion happened. So these are non-electrochemical, but it can complement electrochemical techniques very well. The chapter 4 deals with passivity. Because some materials, including stainless steel and even iron, can develop a passive film if in an appropriate environment. The passive film is a film that's a very thin nanometer scale film. These passive films are usually in the scale of 1 to 5 nanometers, but this can stop corrosion basically, or slow down to a great extent that even if you apply highly grading force, you will not be corroding this due to the small passive layer. It usually comprises of oxide and hydroxide. So we will talk about how this passive film forms and grows, different models that are used to describe this passive film formation and growth, including the major model that we will discuss is the point defect model. How the movement of vacancies can influence the diffusion and migration of these ionic species can influence passive film growth. Chapter 5 will discuss about localized corrosion theory and how localized corrosion develops and how we can avoid it, how to quantify it. So the localized corrosion usually a result of this local break in this passive film, because this passive film, when it is there, the metal alloy is not going to corrode a lot. But if it has a break, this break can be in micron scale, even though I'm showing the passive film is broken, because it is usually not broken to visible extent. You will not see it happening, but this passive film, under this passive film, the metal can continue to dissolve. So you will not be able to notice it until it breaks open or to puts a hole in your component, or it creates serves as initiation for cracking cracks when there is a mechanical load. We'll be talking about different models of how these localized corrosive spots form, and we use some contemporary literature to understand the pitch stability, because here we will be focusing mainly on pitting and crevice corrosion, but we will also talk about the effect of other localized corrosion such as intergranular corrosion and how it might affect the performance. And we will talk about different parameters that quantify the susceptibility to this localized corrosion. So this is chapter 5, I guess. Next, we will be talking about this environmentally assisted cracking. That is an interaction due to stress and environment happening together on the material. So this is a very famous Venn diagram that is used. When there is an environment, it is corrosive, and there is a material, the stress. In this intersection, you will have this stress assisted failure mechanisms or environmentally assisted cracking. You can have this stress corrosion cracking, and similar to localized corrosion. So that's why it is placed right after the localized corrosion phenomenon. We have an internal anodic reaction happening inside the crack, and we have external cathode reaction, and it is a competition between crack growth and passivation, and the passive film is broken. So this is a model of, there are a lot of things going on here. We'll discuss in detail what is happening in the material microstructure, how dislocations and other defects are being generated and retracted, and how this cracking is propagating. And we'll also talk about the effect of cyclic loading in the form of corrosion fatigue, because in real service conditions, the loading is never just static. So it's usually fluctuating loads. So we need to talk about fatigue and different modes of fractures, like whether the cracks are propagating through the grains or along the grain boundaries, and then it can become transgranular or intergranular based on that. So then we move on to high temperature corrosion. So here also we will describe the thermodynamics of high temperature corrosion. Some of you might have taken the corrosion temperature corrosion lab last year, last semester. We will describe the experimental techniques and how these oxides grow at high temperature and what consequences it might have on the material. Here we are talking about the diffusion phenomenon, and this is the gift-free energy versus temperature that gives the stability of different oxides. This is called as the Ellingham diagram, and what happens inside the material where oxygen can get in the material, and the alloy microstructure here. This is a superalloy. So these are relevant for high temperature applications where the temperature, operating temperatures usually exceed more than 500 degrees Celsius. So next we move on to this corrosion and nuclear waste disposal. This will be the guest lecture given by Professor Go from Colorado in the US. We generate a lot of waste. They are classified into different types of nuclear waste that produce the high level. We are mostly interested in this high level waste that are most hazardous because they retain 95% of radioactivity. This is a spent fuel. After you use these enriched uranium for nuclear production, or when you produce nuclear weapons, you generate these spent fuel that needs to be disposed somewhere. So it takes almost some lakhs of years, thousands of tens of thousands of years until this becomes safe. The radioactivity is keeping on falling down, but it takes very long time, like let's say 10,000 years, millions of years to decay. So we need to protect these waste until they are safe. So we need to find dispose. So this is the way they are currently disposing it. There's a temporary storage. These are stainless steel tanks. They put this waste inside it and they live it. So this is not a safe option. So what are all the different options available? There are different methods, different approaches used by different countries, whether to bury this nuclear fuel waste deep under the seabed or create some deep geological repositories and bury it under mountains. So there are different approaches you will learn here directly from Professor Shaulego, who has worked on this nuclear waste disposal himself. So, and then we will be talking about corrosion of additively manufactured alloys and the newly developed multi-principal element alloy. Here I will introduce about my research, what I'm doing here. This is where having a metallurgy knowledge would be very useful. There are a lot of things happening in the material that affects corrosion, how the microstructure of the material influences corrosion, because in additively manufactured materials, there are a lot of heterogeneities that are formed in the material, from the grain structure, the residual stresses that develop on the surface, residual segregation in the dislocation network, and also some processing induced effects such as porosity. So it's very interesting to understand how these several multi-scale heterogeneities is affecting corrosion. And this is another area is what we call as high entropy alloys, multi-principal element alloys, or compositionally complex alloys, depending on different names, there are different definitions. But instead of having a single element, if you talk about iron alloy, iron is the major element. In these alloys, we are talking about cases where you don't have clear-cut majority element that is present in an alloy and how they will influence corrosion. It's a very, really interesting new topic, and we are yet to explore the big composition space that is available. Next, we are moving on to the computational modeling of corrosion. We'll be talking about some physics-based modeling, including density functional theory and how it might be used to understand corrosion phenomena happening in the surface. And as I mentioned, this is the newly developing area is artificial intelligence using this Bayesian network. And there's also modeling of high temperature oxidation using machine learning. So we'll basically introduce you to these topics, and if you want to explore further, I'll also provide some references that you can read during the course of lecture. Then we are talking about the clean energy technologies. Like there is some work that done in FAU on how to perform corrosion experiments for this proton exchange membrane water electrolysis or fuel cells. Bipolar plate, they suffer corrosion. We need to design material that resists corrosion in these new water electrolyzers or fuel cells. And there's also a problem of corrosion in lithium-ion batteries. There is a buzz about electric vehicles, and how corrosion problems will be relevant to the battery technology will be discussed here. So this is all I had to introduce you to the topic. So I'm expecting questions, feedback, anything from this class, or how do you have any questions about the logistics or how this class is going to go? So I welcome question because we have a lot of time left. Almost an hour left. If there is no further question, probably I can start the content, the second lecture. But let me grab my flash drive. I didn't expect this class to be over this quickly. Just some moment, please. So I'm back again. So we'll start discussing the contents of the lecture 2, the basics of corrosion 1, because we'll be covering it in 2 lectures, 2 lecture slide sets, not 2 lectures. We will be talking about the electrochemical nature of corrosion, different forms of corrosion, and we will start with review of corrosion thermodynamics and kinetics, but we will probably get started with the electrochemical nature. Before going into the electrochemical nature of the corrosion, there are different types of electrochemical devices that are possible. That when an electrochemical reaction occurs at a solid interface of electrodes, and electrochemical devices possible. There are 3 kinds of electrochemical devices. The first is the produce material, substance producer, but it consumes energy. For example, if you are doing an electrodeposition process where you are dissolving this copper and depositing in the anode. So you are spending energy, you supply energy, you produce material that you can grow this deposit. You need not have same material here. You can deposit nickel over something. You can deposit many things. Where you here you produce material, you are not losing material because your this anode is the important thing. Where they are producing material by consuming energy, this is electrodeposition. And another example is that where you consume energy, consume substance, but produce energy. That's a battery. So there's a zinc sulfate and copper sulfate here. Zinc is dissolving, and but in this other electrode, which is electrically connected, so here you can connect any device you want, like a light or something, which will go because as the electrons are produced here, it becomes oxidizes into zinc 2+, and the electrons that are produced move through the circuit, and then once the electron passes through the device you want to run, it will glow, and then this electron is consumed at another electrode where this cathodic reaction is taking place, where this copper 2+ in the solution is redepositing as copper on this electrode. So we are producing energy, but we are consuming material because the zinc is dissolving, and you are also consuming copper ions in the solution here. So we are consuming substance, but producing energy. That is a battery. So that's also good in a way. The first 2 kinds of electrochemical devices are good, but corrosion, there is a 3rd kind where you consume energy as well as substance, because you cannot. It is like, for example, you can, if you this zinc wire was directly connected to this copper wire and immersed in these 2 electrolytes, then it is like a short circuited battery that you cannot extract current from it. Only if you can connect something here, you can extract electricity. But if they are directly shorted with each other, then you cannot extract any electricity. You keep consuming copper ions from the solution, and you are also dissolving this zinc plate. So it's a loss in terms of both energy and substance. So here, this is an example of more realistic example of corrosion where you immerse a plate of homogeneous surface into this electrolyte. This electrolyte is nickel. If you immerse this electrolyte material electrode into the electrolyte, what happens is that they start dissolving, but at the same time there is also a counter reaction, that is cathodic reaction, that is happening. So that consumes the electron. So the electron source and sink. Electron source is the anodic reaction which produces the electrons, but they are consumed in some other site within the same material. So in a homogeneous surface, these electron sources and sinks are constantly moving, like they are not constant. Like for example, if metal dissolution takes place here in the first instance, the complementary pair of electron consumption through oxygen reduction reaction or hydrogen evolution might take place here. But you can also have another pair that is happening at the same time. So this is constantly moving sources of electron and electron states. And sometimes when the material is not homogeneous like this is not usually the case. We always have some heterogeneities where we have some stable electron states, some features in the material that are promoting the cathodic reaction, while some features in the material that promote the anodic reaction. So the sources of this separation of anodic and cathodic site in inhomogeneous sample might be presence of some inclusions, like some sort of manganese sulfides that might form on steels, or some precipitates that form in aluminum and magnesium alloys, and even some impurity segregations can and even differences in grain orientation, because different atomic planes dissolve in a different rate. So usually the close packed planes are usually dissolving the slowest thing because their coordination is almost fully satisfied by it, but less open planes in the atomic planes in the crystal might be more susceptible to corrosion. So, and grain boundary and differences in surfaces. So there can be lead design and the step that can form inside the at an atomic level in the surface that can also lead to this specific tendency to promote anodic reaction or cathodic reaction somewhere. And if you have voids, that can also assist in this process. So what are all the requirements in order to have this corrosion process? What are all the requirements? We need a susceptible material, and two, we need a sufficiently aggressive environment. If the environment is not aggressive, if you put some deionized water and stainless steel, the stainless steel might not corrode for a very long time, but you need to have a sufficiently aggressive environment. If you put it in a salt water, it's a different story. So, and you need following elements to form a complete corrosion cell, because the surface, the material which you have immersed in this environment needs to remain overall electro neutral. So you need to have these elements, the cathodic sites on a metal surface that can consume the electrons that are produced, and anodic sites that are the selective dissolution sites, and we need electrolyte that is in contact with the both anode and cathode. This is an ionic contact. I will because you need two circuits. There is an ionic circuit and the electric circuit, the electronic circuit. So they both need to be completely closed for this corrosion process to occur. And of course, there need to be electrical contact between anodic sites and cathodic sites. If you take a piece of steel, they are all already, you see grain boundary is an anodic site and the grain interior becomes cathodic site. They are electrically connected because they are in the same material. But if you immerse in the electrolyte is touching both grain boundary and grain, so there is also ionic contact. So the system is satisfied when you just put a piece of metal in an electrolyte. Usually these are normally satisfied, so this will happen. So corrosion involves oxidation of metal. So what happens is this is the anodic reaction where the metal becomes metal. It releases Z number of electrons and becomes a metal Z plus. Some of the common examples include the iron becoming iron 2 plus and releasing 2 electrons. So this is how this is why I refer to the anodic sites as electron sources, because when iron becomes iron 2 plus, it produces 2 electrons. So these are electrochemical reaction. That is why corrosion is an electrochemical process. So what is nature, what is the definition of an electrochemical reaction? Is that there should be a charge transfer and oxidation state change. So the implication is that material is transformed. Here it was a metallic material and it went to aqueous state into the solution and you produce current. because electrons are released and this current needs to be consumed somewhere. So this pair of reduction and oxidation reactions constitute a full corrosion reaction. It is also commonly referred to as a corrosion cell. So where this is the metal oxidation reaction, and then the water is getting reduced and producing hydrogen evolution. The hydrogen molecule, this is the electron sink. This consumes the electron. This water molecule consumes the electron and releases hydrogen gas and becomes OH minus ion. So this is where what I represented earlier. There is a metal becoming metal glucose ion. It's probably get this as a nickel or iron, which produces two electron process, and these two electrons are consumed here and produces. So again, we emphasize this reaction sites must be both in electronic and ionic contact for corrosion to occur.
How would which side is going to be cathodic, which side is going to be anodic? How does the process typically starts?
So if there is no heterogeneity in the material, any site can serve as anodic or cathodic site. So if you take a piece of, let's assume this is a piece of metal. So if you immerse it, it's fully immersed in the electrolyte, if you imagine. So this site, the metal might start dissolving from this side, for example. And once this metal oxidizes, it becomes ion, enters the electrolyte, it cannot take electrons with it. So electron remains on the metal surface, but it will keep moving, because in a metal, there are free electrons. They keep moving. The electron that the metal has left and become an ion, it moves within the material. At some point, there is also oxygen dissolved in the electrolyte. So this oxygen molecule comes and picks up the electron on the surface, anywhere on the surface, because you have produced some excess charge that needs to be consumed somewhere, because metal does not want to have this excess electron that is produced by the oxidation, so it will consume elsewhere. So that's why I said these sites, the sources and sinks, are constantly moving, and this process happening in milliseconds or microseconds. So at the same moment, maybe the next moment itself, the site where the anodic reaction took place, it can become cathodic pair for some other anodic reaction happening elsewhere on the surface. So this electron source and sink are continuously moving randomly. But for example, this is a normal case where there is no heterogeneity. If there is a heterogeneity, which means there is a precipitate, that precipitate, I will teach you the concept of electrochemical potential in series. If a precipitate composition is such that it is more cathodic, more noble, so then it is more susceptible to promote the cathodic reaction. So the oxygen reduction reaction might be promoted on that particular particle, while the dissolution will take place in the matrix. For example, if we take aluminum copper alloy, in that you can form copper precipitates. Copper is a more noble element and it forms a precipitate. Then this copper surface acts as a preferential cathode. Now there is no movement of the random movement of electron source and sink. There is a fixed electron source, which is the aluminum matrix that dissolves, and the fixed electron sink, that is this copper precipitate. So this is usually called as a microgalvanic coupling. So that's how.
If we have a simple, maybe magnesium metal, but then this process is totally random.
Yeah, it's random.
Any site can act as anode, and
because
maybe it's become a cathode later on.
Yes. Yeah. So that's how on the whole it is uniform corrosion. There is no specific site becoming attacked. And then pure metal without any heterogeneities, if you make a single crystal of magnesium, there's no defect. You have eliminated all defects. This is very hypothetical. If that is the case, then it will corrode uniformly, because on the whole, the net effect which you can observe macroscopically, it will be uniformly dissolving. But if you look at microscopically in a very shorter time span, then the electron sources and sinks are moving randomly across the surface.
Yeah, but only assuming that our metal is fully immersed in electrolyte. Because usually, like in real life, for example, the corrosion still sometimes or often occurs locally because, for example, we need a droplet of water or anything to give the electrolyte.
Yeah.
So,
Oh, now moving on to forms of corrosion. So when these electron sources and things are randomly moving, the net result is you are losing material, the thickness is reducing uniformly, that leads to uniform corrosion. And then we have, if you are welding two metals together. So I already described an example of galvanic corrosion that is happening within the material, where one precipitate acts as cathode and the matrix acts as anode. But a more common example is welding. Like if you weld some aluminum to copper, for example, again, now it is not happening in the micro scale, but it is macro. Or if you weld zinc to steel, zinc is more active metal. So then the active metal gets consumed at the expense of a noble metal. A noble metal will not, it will stay intact because this is supporting just the cathodic reaction, which is basically either oxygen is reducing there or water is reducing there. But here this active metal selectively undergoes corrosion. So you are losing active metal at the expense of noble metal. So this is galvanic corrosion. And sometimes there is another form of localized corrosion. It's crevice corrosion. When you have some rivets, like if you screw a metal screw over another material, you create a small gap where the electrolyte can move in, but it gets trapped there. There is a stagnation, and you have, as dissolution takes place, the metal becomes much more concentrated, and it continues to attack locally under this crevice. This is a stagnated region. And then another form of localized corrosion is when hydrogen gas, maybe resulting hydrogen sulfide or something at higher temperature attacks, and you can create surface cracks. How these cracks form, we will discuss in the environmental assisted cracking part. But you can also create voids when hydrogen interacts with the material. It can really be problematic. So then another form of corrosion is intergranular corrosion, where grain boundaries are selectively attacked because it might be due to depletion of some alloying element that promotes passivity, that the grain boundary suddenly becomes not passive and it preferentially gets attacked. A classic example is the example of sensitized stainless steel, where you can precipitate these chromium rich carbides at the grain boundary. That means you are consuming chromium atoms to carbides, so they form carbide. Around the carbide there is not enough amount of chromium to form this passive film, because in stainless steel it is the chromium alloying that makes stainless steels actually stainless, because you need to have sufficient, which usually people say you need 12% chromium to form a passive film. Pure iron is not under normal conditions, it is not really passive. Maybe in sulfate containing environments, iron is also passive, but in real environments, iron tends to corrode. So you add more chromium to the material. If you have at least 12% chromium, then you are able to form this very thin nanometer thick oxide scale or film that protects the material. So then the passive film forms. In the case of intergranular corrosion, the passive film is absent in grain boundaries. So now without passive film, they should continue to corrode. So you can see the grain boundaries are selectively attacked, and sometimes these grains, individual grains in the material may fall off and can create significant damage. So I discussed about the micro galvanic effect and the macro galvanic effect, but it can also happen so that at atomic level there is galvanic corrosion happening. If you have a brass alloy, which is copper zinc alloy, where copper is more noble element, zinc is less noble element, they are not forming any precipitates. They are still in complete solid solution, and the atoms are randomly distributed. The zinc atoms are randomly distributed in the copper, so you expect, and if you assume that there is no other heterogeneities like the boundaries or something, these atoms itself at atomic level, copper can selectively remain, and can remain as a cathodic site, where zinc will alone continue to dissolve. So you start forming some porous layer because you are losing some atoms selectively. Then you form this nanoscale porous layer where you are just left with some copper porous layer instead of this called as de-zinkification, where zinc is selectively removed from the material. So this is also called as de-alloying, because locally in this region you started with some 25% zinc, but in this local region, as zinc is alone selectively dissolved, you might end up with 5% zinc or even without zinc at all. So this is de-alloying, opposite of alloying. So this is de-alloying. And then another famous form of corrosion is pitting corrosion. This is so this and Krebs corrosion have shared some similarities. Like here, because of this stagnation, you start to create a very concentrated environment locally, and the material continues to corrode. But here, the sample surface is boldly exposed. There is no stagnation, there is no rivet. But if a passive film locally breaks down, and underneath the passive film, the slightly broken passive film, if the environment continues to evolve and become more concentrated, then it can result in same thing what has happened. But like this, you can go inside very deep, you can even drill hole. Usually crevices tend to be shallower than pits due to the rivet arrangement. So I also like to call crevice as a ready-made pit, because you already created what is needed for a pit by the external means of rivets and stuff. So, but we will discuss more detail about pitting and the corrosion later. And but we said erosion or this damage due to friction are not generally considered in corrosion, but some people do consider them when they occur together with an environment. Like if you just impinge a particle and erode the surface, that is not corrosion. But if there is an environment, if you're using salt water and at the same time you are impinging a slurry of material, then there is an erosion corrosion that can occur together. So wear is just if you rub two solid surfaces together, it's wear. But if during this rubbing action, if there is an electrolyte that is involved, that is also dissolving the material, that is probably aiding the wear and accelerates the wear, that can also happen. That is fretting. And these are different forms of environmentally assisted cracking, like corrosion cracking, corrosion fatigue, and hydrogen induced cracking. So that's all with forms of corrosion. So now we will try to understand how current flows in electrolyte. We know how current flows inside metal, so how the electron moves all must be familiar from probably high school or later, but this is current flow in electrolyte. The electrolyte, the current flows by ionic transport. Again, Faraday's law governs this ionic current. This is related to the ionic current, is related to the ionic flux, how much ions move. So this is the charge per mole of electrons. There are three ways that ions might transport in electrolyte. Why I am talking about this ionic transport of electrolyte is that when I go to teach pitting corrosion and other forms of localized corrosion, because this ionic transport must always balance the electron transport that is happening. Sometimes the rate of metal dissolution might exceed how much the ionic current can dilute. So then you start to concentrate it. So that we need to understand how the current flows. When there is a current imbalance, then there is accelerated corrosion happening. So that's the reason why I am introducing this current flow in ionic liquids here. It's not really ionic liquids, it has a different meaning, but here we're talking about electrolytes, ion transfer electrolytes. So convection is just if there is a density gradient or temperature gradient within a normally stagnant stream of water, then there is a convection, and related to the velocity of the liquid and the flux of ionic species is just a product of the concentration and the solution velocity. What was the concentration of the species of ions and how much is the rate of flow that is happening? So simply then you can apply Faraday law, this N of J is the flux, and N is the number of electrons, the electronic state, the value state, and then this is the Faraday's constant, and then you can, like if there are multiple ionic species, then you multiply with the charge into the ionic species concentration for NiCi, the summation of it, and you get the flux. Most common ion transport mechanism is diffusion. It occurs down the concentration gradient. You have more positive ions, this of the same charge, this is independent of charge. If you have more cation concentration here and less cation concentration here, the diffusion of positive ions is going to take place in this direction. So that's why you always have this negative sign, because you are going against the concentration gradient. So this is a fixed first law and second law that are two. This is steady state diffusion where the flux is, and this is the non-steady state transient diffusion where concentration is changing as a function of time. So another thing that can happen is that you have an electric field, and these ions can move in the electric field if there is a, for example, if there is a positive potential and a negative potential, you apply a battery to two metal plates and in between electrolyte. You will see the positive ions are moving towards the negative electrode, and the negative ions are moving towards the positive electrode. This is due to the electric field. So this is migration. So this you must know. And now we are going to, before we jump into corrosion thermodynamics, we will introduce the concept of concept of electrochemical potential. Because if you take at equilibrium, if you just have a beaker of electrolyte, the charges are randomly oriented, but when you put insert a metal inside this electrolyte, if you immerse this metal, so what happens is that the corrosion always occurs as this interface, and all electrolytes, there should be some solid interface that must be there. This discontinuity that is associated, because as far as the electrolyte is concerned, this is a discontinuity. You have inserted a metal in between. So this electrolyte sees this metal surface, you can consider that as some obstacle or heterogeneity. So this redistributes the charge. So the charge is redistributed. The interface on the whole is neutral. That is, we are not violating electroneutrality principles, but locally they are distributed. So this charge that is redistributed is the source of a potential drop that is there, because there is we see the surface of the metal is positively charged, and you develop a negatively charged. This is locally, this is happening at a very small thickness, probably in tens of angstroms, but there is a very strong field that is created, because when you have a dipole, there is always an electric field that is created. So that creates a potential drop at the electrode surface. There will be excess of one side of charge. Directly next to the electrolyte, there will be excess of opposite charge. If the surface is negatively charged, you will develop a local positive charge very close to the surface. This is not in this scale. This is not drawn in this scale. This is happening at very, very small thicknesses. That is what we call as electrochemical potential. Actually, it is a potential drop, but we call it as potential. So it is impossible to say, measure the value of absolute value of electrochemical potential. We can measure it only with the help of reference electrodes. So there is if you have a metal electrode immersed in the solution, as I said, there is a metal solution potential drop, but you also have something called a reference electrode, and it also has its own potential drop. So what we measure is the difference between the potential of the reference electrode and the metal surface. So the voltage difference between the reference electrode is the measure of potential drop at the sample electrode interface, electrolyte interface. But we have arbitrarily fixed that the hydrogen evolution reaction happens, the half cell reaction happens at 0 volt. So if we have a standard hydrogen electrode, which we will discuss, it is set as 0, whatever potential you measure is considered to be the electrode potential of a half cell. So we will discuss more about these half cell reactions in the next lecture. So thanks for your attention, and if there is any further questions.